Hello, welcome back. We were discussing the node analysis. In continuation with that, so we will now solve some problems related to node analysis. So this is the problem. So use node analysis to find voltage Vx in the circuit shown in figure 18. So this is the figure 18 and you need to find this voltage, okay, Vx, and this Vx you have to find using the node analysis, right. And now first step what we need to do in the case of node analysis is to identify the ground node, okay, and how many nodes actually we are seeing here. So as let me redefine what is actually a node. A node is that point where two or more circuit elements join. So now this circuit element, this circuit element, this circuit element join at this point. So this can be one node and this can be the other node, okay. So node 2, so this can be the other node because this circuit element join here, and this can be the other node, okay, and this is the last node. But what we really consider, okay, here is the node, those nodes where three or more circuit elements join, okay. So that means we are not considering the node and the voltage here and the node and the voltage here, for the simple reason that later we are going to apply KCL here as well as here. That will simply increase the number of equations, and without them also we will be still able to find the response in the network. So we will be considering only those nodes, okay, and the corresponding voltages, okay, only at those points, okay, where three or more circuit elements join, okay. So that is, this is the ground node, let me consider, and this is the one of the nodes, other nodes, and this is the second node, let us say, okay. So why we are not considering this and this as the part of the analysis, as the node analysis part? For the simple reason, without being applied the KCL here as well as here, still we will be able to find the response at any point of network. So we will consider the those points where three or more circuit elements join to be the nodes and their node voltages, okay, right. So now this is the problem given to us, okay. So what we will do, so let me go back to the board here. So the same problem has been written, and now this will be the first job is to identify the ground node. So this is the ground node where the potential is considered to be 0, and the remaining nodes 1 and 2. This and this we are not considering because without applying KCL there we will be still able to find the response at any point of network, okay. So we are considering only those nodes where three or more circuit elements join, right. So now this is V1 to V2. So what are these? These are the voltages associated with node 1 and node 2 respectively. Let me reiterate that this is the potential difference between this point and this point with ground as a reference, and V2 is the potential difference between this point and this point, or potential difference between this point and the ground point with ground as a reference, okay, right. Now what is our objective? Our objective is to find Vx. So, okay, so what is Vx in fact? So Vx is the potential difference between this point and this point, okay. You are observing plus here, minus here, so this is considered to be at higher potential point and this is the lower potential point, okay. So Vx, you can also consider that to be the potential here with respect to this, even you can say so. Now Vx can be found by considering the potential difference between this point and this point. Now what is the potential here? What is the potential here? Now please remember, when we are considering the potential differences, these two potentials should be with respect to the same point. Now in our case these two potentials will be with respect to this ground point. Now we know the potential here with respect to ground is V1, and when we come here potential would have increased by 5 volts because of there is a presence of source. This is the indicative of what? As compared to this point is higher in potential by 5 volts. So the potential here with respect to the ground is V1. When we come here potential would have increased by 5 volts. So the potential here will be V1 plus 5. If you say 5, it is the potential difference between this point and this point, okay. It is now when we take the potential difference, as already told, it has to be with respect to ground point only. So the potential here with respect to ground would be V1 plus 5 then the potential here, okay, is V2. So, the potential difference would be V1 plus 5 minus V2. So, if you know the node voltages V1 and V2, it is easy to find Vx. And also one more observation. Now, whenever there are voltage sources in the node analysis, let us all be very careful. Just like whenever there are current sources, we should be careful in the case of mesh analysis. In the same way, whenever there are voltage sources in the case of node analysis, let us all be very careful. Now, what you observe, this one already dealt with. Now, you are observing what? This voltage source. This is the voltage controlled voltage source. Now, you are observing what? That this is connected between node 2 and the ground. And after all, what is node 2? The voltage. What is the node 2 voltage? It is the potential difference between this point and this point. And so is 2Vx. Okay, and this has got the reference as ground, and even this has got the reference as ground. So, what we can say, V2 is straight away 2Vx, and we can write it as 2 times of V1 plus 5 minus V2. Now, this implies, okay, I can now 2V1 minus 2V2, this can come here. So, 2V1 minus 2V2 minus 3V2, and then there is what 2 into 5 10. So, this goes to the left hand side, or in this case we write it on right side. So, minus 10. Okay. So, 2V1 plus 10 minus 2V2 minus V2. So, minus 3V2, this 10 will come to the left, becomes minus 10. So, call this as equation 1. Call this as equation 1. Now, we have already obtained what? V2 expression, okay, V2 as 2Vx. Supposedly, if there was 10 volts, we would have written V2 is equal to 10 volts. Now, when we know the value of V2 already, or whenever an equation associated with a node is already obtained, you need not again apply KCL at that node. It will be redundant. That means, without applying KCL, we still will be able to find the response at any point of network. Now, we got an equation, something related to what? The node 2. So, again we will not apply KCL at this node. Yeah. So, 2V1 minus 3V2 is equal to minus 10 is nothing but equation 1. Now, we will apply KCL here. Okay. So, apply KCL at node 1. Now, we will strictly follow the statement of the KCL, the algebraic sum of branch currents that leave a node is equal to 0. Now, what is the current? There are 3 branches associated. So, what is the current that comes out of this node in this direction? In this direction. So, it is nothing but potential difference between these two divided by resistance. Supposedly, this is a resistance. Now, this is what? Conductance. So, what we should do? The potential difference between these 2 points into 3. Now, the potential here is known, V1. The potential here, very easy. The potential here is ground. When we come here, potential would have reduced by 30 volts. So, the potential here is minus 30 with respect to ground. So, what is if I want to find the current that flows in this direction, so it is V1 then minus the potential here into 3 because of this conductance. So, I should write it as V1 minus of minus 30 divided by is correct whenever this is a resistance. Now, this is what? The conductance. So, multiplied by 3. So, this is done. Now, what is the current that comes out of this node in this direction? So, it is nothing but when it is the current that same current which flows through 2 more conductance, the potential here minus the potential here into 2, because we are considering the current to flow in this direction. So, the potential here is what? As already told, it is V1 plus 5, then the potential here is V2. So, the potential difference would be V1 plus 5 minus V2, then into 2. You could have also written Vx into 2, no problems. But again Vx is unknown. So, along with V1 and V2, Vx will be one more unknown. So, let us not write that way. So, we will represent in terms of node voltages only. So, these 2 branches are done. Now, whatever the current that comes out of this node in this direction. So, that is 4 amperes. So, 4 is equal to 0. Now, when I arrange this equation, so this is 3V1, 2V1. So, 5V1, then minus 2V2, minus 2V2, that is all I think, yeah, minus 2V2, then minus into minus 30, okay, 30 into 3 90, 90 plus 10 100 plus 4 104 is equal to 0. So, then this implies 5V1 5V1 minus 2V2 is equal to minus 104. Call this as equation 2. Call this as equation 2. Now solving 1 and 2. Solving 1 and 2. We get so V1 as minus 26.545 volts, then V2 as minus 14.363 volts. Then our objective is not only to find V1, V2, main objective is to find Vx. So Vx is given as, in the very beginning we have written that as V1 plus 5 minus V2. So V1 plus 5 minus V2. So Vx we get it as minus 26.545 plus 5. Then there is minus here and there is minus here. Minus into minus plus. So plus 14.363. So then this implies Vx is equal to minus 7.182 volts. Okay, so this is how we get the value of Vx, and Vx how it has been found now using the node analysis. Okay, right. So that ends this particular problem. Okay, right. Now we will go to the next problem. So that's what has been given here. So this was the ground node, V1, V2 identified, then the equations whatever we have seen, 2V1 minus 3V2 minus 10, so that is this equation, and then 5V1 minus 2V2 minus 104, that is what is this equation. So when we solve, so we get V1 as minus 26.545, V2 as minus 14.363. So when we try to find Vx, it will be something like minus 7.182 volts. Now this negative basically indicates, right? Now had this been positive, it would have been represented like, as with respect to this point is higher in potential by 7.182 volts. Now with the negative, what we can say is, with respect to this point is lower in potential by 7.182 volts. That means the actual positive polarity is at the right, the actual negative polarity is at the left. But no problem, since it has been already identified in the problem, so it just gives the idea of the actual polarities of the voltage drop of Vx. So that's it. So we will go to the next problem now. Okay, so the next problem is find the power delivered by dependent source using node analysis in the circuit shown in figure 19. So now this is the network given to you. You have to find the power delivered by this particular dependent source. Okay, yeah. Now we have the copy of the problem here. Okay. Okay. So now, oh yeah. So this is IA. It is given in the problem. Now we need to find the power delivered by this voltage source. Now we have to use the node analysis. Okay, first we will identify the ground node. So this is the ground node. Leaving this ground node, in actual there are what, 1, 2, 3, 4 nodes leaving this ground node actually. But as already told, we are neglecting those nodes where only 2 circuit elements join, like this as well as this. Okay, for the simple reason that without applying KCL there, we will still be able to find the required responses. So we will consider only those nodes where 3 or more circuit elements join. If you go by that way, so you have only one node leaving the ground node existing. So we will identify the corresponding voltage as V1. Okay. Now PDS, so power delivered by the dependent source, is given as what? Long back it has been told that it is nothing but the voltage source value 60 IA multiplied by that particular current which comes out of the positive polarity, that is this current. Okay, so let me call it as, say, Ix. Okay, let me call it as Ix. So Ix, so 60 IA Ix. Now we will find the node voltage, and using that we will be able to find IA and Ix. Now it is very much obvious from the circuit. Okay, from the circuit PDS is given by this, and also from the circuit IA is equal to, the current is flowing from top to bottom. So, this potential minus this potential, this time it is resistance. So, this potential minus this potential divided by 20. The potential here is V1 with respect to ground is, and then the potential here with respect to ground, in fact it is the ground point 0. So, V1 minus 0 divided by 20. So, it is just V1 by 20. Now, what is Ix? What is Ix? Now, this particular arm, this particular arm, it's a series arm, whatever we are seeing. Okay, so now this arrangement can even be viewed to be something like this. For the sake of convenience, I am writing. Now, if I alter the positions of the circuit elements in a series arm, the current is not going to change. So, that we have to remember. So, V1, then we have what? Minus plus 60 IA, then we have what? 10 ohms, then we have 15 ohms, then we have ground. So, still the current that flows through this arm will be Ix, no doubts in that. Now, how to find Ix? Ix is the current that flows through 10 ohms and 15 ohms. Now, these two is a series combination, so I can write it as 25 ohms. So, the Ix is given by this potential minus this potential divided by 25. The potential, please remember, with respect to ground, we have to find the potential here is V1. When we come here, the potential would have increased by 60 IA, very much indicative here. Okay, so V1 plus 60 IA is the potential here with respect to ground, because the potential difference between these two is 60 IA with this as reference. Okay, if the potential here is V1, the potential here should be what? Increased by 60 IA as compared to V1. So, the potential here is V1 plus 60 IA, and the potential here, it is the ground point 0. So, Ix should be now V1 then plus 60 IA and then minus 0, I am leaving that. So, V1 plus 60 IA minus 0 divided by 10 plus 15. So, or we can say Ix is V1 plus 60 IA divided by 25. So, now you can observe IA can be represented in terms of V1 and Ix can be represented in terms of V1 and IA in terms of V1. So, if we find the node voltage, it is as good as finding what? The required thing, that is the required parameter PDS. Okay? Yeah. So, now apply KCL at node 1. There is only one node. Okay. So, we will strictly follow the statement of KCL. The algebraic sum of branch currents that leave a node is equal to 0. So, what is the current that comes out of this node in this direction? It is IA, strictly speaking, but it can also be written in terms of node voltage. So, this potential minus this potential divided by 20, or V1 by 20. Now, what is the current that comes out of this node in this direction? So, V1, what is the potential here? The ground potential is 0. So, when we come here, potential would have increased by 40 volts with respect to ground. So, the potential here is 40. So, the potential difference, okay, when we consider the current that flows in this direction, would be V1 minus 40 divided by 5. And then what is the current that comes out of this node in this direction? It is Ix only, but we have written already Ix value here as what? V1 plus 60 IA, okay, V1 plus 60 IA divided by 25, and this is equal to 0. Okay, right. And now we need to solve for V1. Okay, so we know that IA is V1 by 20. So, substitute in the above equation. So, this implies V1 by 20 plus V1 minus 40 divided by 5, and then plus V1 plus 60 into V1 by 20 divided by 25 is equal to 0. So, 2 1s are 3s are, and then you will have what? Okay, V1 plus 3 V1, 4 V1. Okay, this 20 and 60, 21s are 23s are. Now, the LCM when I observe, it is 100. So, this implies 100, and then what you can do, V1 5 V1, you know how to write this, and this 20. Okay, so 20 V1 minus 800, okay, by virtue of the multiplication with 20, okay, because 5, you know, it goes 20 times, okay, in 100. So next you have 4 V1 has to be multiplied to 4, so 16 V1. Now this is 0. Now you can also write this as what? This 100 multiplies this 0, so you will be left with what? Okay, so 20, so you will be left with only the numerator. Then simplifying that, so 25 plus 16, 41 V1. Okay, then this goes to the right hand side, 800. This implies V1 is equal to 800 divided by 41. So which gives you 19.512 volts. So which gives you 19.512 volts. Now let us calculate IA and IX. So IA is now equal to V1 by 20. IA is now equal to V1 by 20, and it is given as 0.9756 amperes. Okay, right. So now we will take this and substitute in the PDS expression. Okay, right. So PDS was found to be what? Let me rewrite. So 60 IA into IX, and 60 IA, and IX was written as what? It is V1 plus 60 IA divided by 25, and then 60 IA, and you know IA is V1 by 20, so by virtue of that you will have what? 4 V1 by 25 here. Okay, so you know IA is V1 by 20, so this becomes 3 V1 plus V1, so 4 V1 by 25. So when we substitute PDS, okay, so 60 into 0.9756, then 4, then V1 is 19.512, then whole divided by 25. So we get PDS as 182.74 watts, and the power delivered value is positive. It simply means that in fact the current IX, okay, in reality comes out of the positive polarity. So that means it is actually delivering the power. So power is actually delivered. Okay, right. So that's the problem. Okay, so that's what has been written here. Solution: identify the ground node and other node with its voltage as shown. Same thing from the circuit IA. So then PDS, okay, 60 IA multiplied by that current that comes out of positive polarity of 60 IA, and then you have what? 60 IA, then V1 plus 60 IA by 25, and then similar, I mean apply KCL at node 1. So just what we did there, okay, it is appearing here. Okay, and finally we get what? 182.74 watts of power delivered. Okay, yeah. Now we will go to the next problem. Okay, and here what is our objective? Find the current I1 in the network shown in figure 20. So this is the figure 20, of course not being represented. Yeah, this is the figure 20. So use node analysis. Okay, and I1, where it is this current, and this current has to be now found using the node analysis. Okay, and what is the source here? 20 cos 4t. Okay, now let us recall the phasor representation of the AC sources and responses. So we will use them and find the node voltages V1 and consequently the value of I1. So identify ground node and other node voltages as shown. Okay, so this is the ground node, and 1, 2. Okay, so these are the node voltages. Okay, so this is the ground node, these are the node voltages V1 and V2. Okay, yeah. Now let me write that network on the board. So you have so 20 cos 4t volts, then you have 10 ohms, then you have minus J 2.5 ohms. Okay, this is the impedance of the capacitor, and then this is the current which we need to find. Then J4, then we have current source, dependent current source 2I1, and then we have J2 ohms. So, we have identified this point to be the ground node, and leaving this ground node the other nodes, that means those points where 3 or more circuit elements join, this one as well as this one. So, V1, V2. So, we will apply the node analysis to find I1 now. And now, what we need to remember is, we have to be very sure of the objective. Our objective is to find I1. So, from the circuit, so I1 is now equal to, it is the current that flows through this impedance. So, this potential minus this potential divided by the impedance. Impedance has got the unit of ohms. Now, V1 potential here is 0. So, V1 by minus J 2.5. So, if we find V1, it is as good as finding what? The I1. So, let us find that. So, we use the node analysis here. So, all the passive circuit elements are represented using the units ohms. Okay, then 20 cos 4t, now its phasor representation. Okay, whatever I am writing is implies, please note that. Okay, so 20 cos 4t in phasor form is nothing but 20 at an angle of 0 degree, because the phase is 0, and then 20 at an angle of 0 degree volts. Now, we will apply KCL. Okay, apply KCL at node 1. What is the current that comes out of this node in this direction? It is V1 minus 20 at an angle of 0 degree divided by 10. Then what is the current that comes out of this node in this direction? It is I1, no doubts in that, but simply it will increase the unknown along with V1 and V2. So, we will still write in terms of node voltage only. So, V1 divided by minus J 2.5. Then what is the current that comes out of this node in this direction? So, it is V1 minus V2 divided by J4. So, will be equal to 0. And now, the best method is to calculate what 1 by 10, 1 by minus J 2.5 and 1 by J4 using the calculator, and they will become what? The coefficients of these terms. So, when you do so, this implies, so 0.1 V1, and then 20 divided by 10. 20 at an angle of 0 degree is just what? 20, because 20 cos 0 plus J 20 sin 0. Sin 0 is 0. 20 cos 0 should be what? 20. So, minus 20 divided by 10 is 2. Then 1 by minus J is J, and 1 by 0.25 is 0.4. So, it will be plus J 0.4 V1, and then 1 by J is minus J, 1 by J is minus J, 1 by 4 is 0.25. So, minus J 0.25 has to be multiplied. So, minus J 0.25 V1, and minus into minus plus J 0.25 V1 V2 is equal to 0. Now, accumulating the terms related to V1, you have what? Point V1, J 0.4, then J 0.25. So, these two, when you take the difference, it will be plus J 0.15 V1, and this is 0.1 V1, which is the real part. So, this implies, so 0.1 V1, then plus 0.1 plus J 0.15 V1, next plus J 0.25 V2, and then you have minus 2 here, which goes to the right hand side and becomes plus 2, and this is the equation 1, and this is the equation 1. Now, apply KCL at node 2. So, node 2 is here. So, what is the current that comes out of this node in this direction? So, V2 minus V1 divided by J4. What is the current that comes out of this node in this direction? Minus 2I1 Okay, and what is the current that comes out of this node in this direction? So it is V2 divided by J2, which will be equal to 0. So this is the KCL equation. And now you know 1 by J4, you know, can 1 by J is minus J 0.25. So minus J 0.25 V2 plus J 0.25 V1, and then minus 2. What is I1? I1 in the very beginning we have declared it as what? V1 divided by minus J 0.25. So V1 divided by minus J 2.5 rather, and then lastly plus V2 divided by J2. V2 divided by J2, we will write this as it is, equal to 0. Okay, now this one minus into minus plus, and you know 2 divided by 1 divided by J is minus J. So 2 divided by 2.5 is 0.8. So we will write that. So minus J 0.25 V2 plus J 0.25 V1, and this will be minus into minus plus, minus minus cancel, rather plus, then 1 by J minus J 0.8 V1, and this will be 1 by J minus J, and 1 by 2 is 0.5. So minus J 0.5 V2 is equal to 0. Now V1 terms are here. So minus J 0.25 minus 0.8. So minus J 0.55 V1, and then minus J 0.75 V2 is equal to 0. Call this as equation 2. Now using Cramer's rule, we are using Cramer's rule, okay, wherein the delta is now given as 0.1 plus J 0.15, then J 0.25. So that is the second term here. Then here, so minus J 0.55, and then minus J 0.75. Then this can be written as 0.1 plus J 0.15 into this minus J 0.75. Then there is inherent minus here, so that will be minus J square multiplied to minus plus J square, so minus, okay, so 0.25 into 0.55. So let me tell this again, there is inherent minus this into this, minus into minus plus J square is minus, so minus 0.25 into 0.55. So when you use the calculator and find, you will find this to be minus 0.025 minus J 0.075. So this is delta. Now delta V1, because we want I1, that has to be kept in mind. So we need to find V1. So for that you require delta V1. So the right hand side of the equations to be substituted in the first column here. So 2 0, then J 0.25, then minus J 0.75. Then this is equal to minus J 1.5. So this implies V1 is equal to delta V1 divided by delta, so which is equal to minus J 1.5 divided by minus 0.025 minus J 0.25 minus J 0.075. So V1 is now given as you will get it as 18 plus J6. You can also call it as what? We will represent in the polar form, which actually gives you more meaning. So 18.97 at an angle of 18.43 degrees volts. But our objective is to find I1. So I1, we know in the very beginning we have written it as I1, so which is V1 divided by minus J 2.5. So I1 is equal to 18.97 at an angle of 18.43 degrees divided by minus j 2.5. In the calculator you have to substitute, okay, the numerator in the brackets. Even the denominator should be in the brackets. So I1 is now equal to, when you do so, okay, so the I1 will be equal to 7.589 at an angle of 108.43 degrees amperes. Okay, so this is the phasor representation of the current I1 that flows through the capacitor. That means, at our point of reference t is equal to 0, this has got the amplitude of 7.589 and traces the angle of 108.43 degrees at our point of reference t is equal to 0. So in general, if I want to write the steady state expression I1 of t, I have to write it as 7.589, and since the function was cosine function, so we will take the same thing, cos. Had this been sine, you would have written sine here, cos, then you have 4t plus 108.43 degrees in amperes. So this is the I1 of t, okay, and this is the I1 in phasor representation. Okay, so that is the end of this particular problem. Now we have solved the problems related to the node analysis. Now we will go to the concept of supermesh. We will go to the concept of supermesh, which is interesting anyway, right? So and what we have to remember is concept of supermesh. Alright, now we will see some of the things related to supermesh now. Concept of supermesh. When this supermesh concept needs to be applied, supermesh concept is considered whenever a current source appears in common to two meshes. Here you see, this is one mesh, this is another mesh, and you observe a current source to be appearing in common to two meshes. In these cases, if we apply the concept of supermesh, then we will see reduction in the number of steps to obtain the solution of the network. Okay, so let me illustrate the advantage of the supermesh by considering this particular example. Okay, right. So Vs, then you have R1, then you have the current source, so Is, then you have R2, and then R3, and the preliminary objective in the mesh analysis will be to find the mesh currents. So we will find the mesh currents first by the usual method of mesh analysis, next by using the concept of supermesh. Okay, so first by ordinary method of mesh analysis. So apply KVL to mesh 1. So R1 I1 plus, the potential drop across the current source, it depends upon the circuit which we are using. So right now we don't know the potential drop across the current source, so we will identify it as Vx, one more unknown invariably. So plus Vx minus Vs is equal to 0. Then this can be written as R1 I1 plus Vx is equal to Vs. Call this as equation 1. Next, apply KVL to mesh 2. So when we apply KVL to mesh 2, R2 I2 plus R3 I2 minus Vx is equal to 0. So then this can be easily written as Vx is equal to R2 plus R3 into I2. Call this as equation 2. Now equation 1 and 2 we have. Now there is one more equation which we can think of. What is that? Take this, and substitute here. Okay, substituting 2 in 1. So what do we get? So R1 I1 plus, Vx is substituted. So R2 plus R3 I2 is equal to Vs. Call this as equation 3. Now you have, this equation resulting from these two equations. So in effect you can say there is one equation and I1 and I2, two unknowns need to be found. But you also see what? The relationship between I1, I2 and Is from the network. So, from the network, what we observe, you know, you have to remember this current source in whichever branch it is present, it will see that current in that branch is the value possessed by the current source. So, the current in this particular branch is Is and it is the resultant of I1 and I2, and I2 is in alignment with that, I2 is opposite to that. So, you can say Is is I2 minus I1, okay, and this you can write it as I2 is equal to I1 plus Is, call this as 4. And now, you know, substituting 4 in 3, okay, that is I2 in 3, we get what? We get value of I1, and obtained value of I1, substitute I1 in 4, we get what? We get I2, So, thus by using the usual method of mesh analysis, we were able to obtain what? I1 and I2. Now, let me illustrate the advantage of the super mesh, okay, right. Now, using the concept of super mesh, first what we do is, we will identify, oh, that there is a current source appearing in common to two meshes. So, then obviously the relationship will be existing between what? The current source value and the corresponding mesh currents. So, we will call that as constraint equation. So, from the circuit, so first let me write that as Is is equal to I2 minus I1. So, this implies I2 is equal to I1 plus Is. Call this as equation 1. Okay, so, we have identified the current source to be appearing in common to two meshes, and we have written the relationship that exists between the corresponding mesh currents and the current source. After doing this, we will club the corresponding mesh and call it as a single mesh, which is referred as the super mesh. Now, this is the super mesh. What we have done, we will virtually remove the arm of the current source, and when we do so, these two meshes will be clubbed, and the resulting mesh we will call it as a super mesh. And please remember, we will not allocate a separate current to super mesh. If we are applying KVL here, the current will be still I1. If we are applying KVL and considering the potential drop across R2, the current here will be still I2. So, there is no separate current allocated to super mesh. Let us remember that. So, what we have done, we have written the current source, okay, we have written the relationship that exists between the current source and the corresponding mesh currents. Then we have virtually removed the arm common to two meshes, which resulted in clubbing of two meshes, and that clubbed mesh, okay, so will be referred as the super mesh. And then we will apply KVL to the super mesh. So, apply KVL to super mesh, and let me identify the super mesh: R1, R2, R3, then Vs, then back to R1. So, now when I do so, R1 I1, the potential drop here, plus R2 I2 plus R3 I2, so we have come here. Now, minus Vs is equal to 0, and then this implies, you know, R1 I1 plus R2 plus R3 into I2 is equal to Vs. Call this as equation 2. Now, you observe equation 2, it is same as equation 3 in the previous case, R1 I1 plus R2 plus R3 I2 is equal to Vs. Same thing here. But to get this 3, we wrote 1, 2 and then substituted 2 in 1 to get this. But here, by simply applying KVL to super mesh, we were able to get this. So, in effect, this has reduced what? These two steps, right. So, then what is there? Our objective is to find the mesh currents. So, we have two equations and two unknowns I1 and I2. So, easily the mesh currents can be found. So, for the sake of completeness, let me write that also. Substitute 1 into to get value of I1 and substitute I1 in equation 1 to get value of I2, right. So, that is how we can use the concept of super mesh, right. And definitely in this case super mesh, when we consider that, it has reduced the number of steps in obtaining the solution. So, in due course if we see any problem, okay, and if we have to solve that by using mesh analysis, and if we observe that there is a current source appearing in common to two meshes, we will use the concept of super mesh, okay, right. So, the problems related to the super mesh, we will see them in the next class. So, today we have covered the problems related to the node analysis and the illustration of the advantage of using the concept of super mesh. So, remaining things we will take up in the next class. Thank you.